In this video, we're going to talk about the Fischer esterification reaction. I'm going to start off by talking about the reaction conditions that we're going to be using, and then we're going to go through a detailed look at the mechanism. So let's take a look at what's happening in this reaction. We're starting off with a carboxylic acid. We're going to react this with methanol. We're trying to form a methyl ester in this particular case. So the other side product that we're going to be getting is methanol. Now if we look at the carboxylic acid, this is one of the least reactive carboxylic acid derivatives that we have. And if we're looking at methanol, methanol happens to be a pretty weak nucleophile. So we have a weak nucleophile, and we have a weak carboxylic acid derivative. So we want to do something with our reaction conditions to try to get our chemistry to work. So in this case, what we're going to be doing is we're going to be adding an acid catalyst. So I'm going to use paratoluene sulfonic acid in this case. With an acid catalyst, we can activate the carbonyl of our carboxylic acid, and that's going to allow our weak nucleophile, the methanol, to be able to attack that carbonyl and undergo this reaction. In the next step, we're going to take a detailed look at the mechanism of this reaction. So now let's take a detailed look at the mechanism of this reaction. So we have our carboxylic acid, and we're first going to react this with our acid. So here's our paratoluene sulfonic acid. So we're going to protonate that carbonyl, and this is activating that carbonyl. It's going to make it much more reactive. Once we've activated that carbonyl, then we can have our methanol attack. So methanol attacks our carbonyl, just like we've seen in our other nucleophilic acyl substitution chemistry. This is going to give us a tetrahedral intermediate. But now we want to make one of these alcohols a better leaving group. And the way we've done that in the past is by protonating them. And we have a good acid within the same molecule. So we're going to do an intramolecular proton transfer to make one of these alcohols a better leaving group. Now that we've made it a better leaving group, we can try to reform our carbonyl and kick off our leaving group. So we're going to take one of these lone pairs, reform the carbonyl at this position, and kick off that leaving group. That gives us a protonated ester and also some water. Now to get to our final product, we need to deprotonate this. And we can either use the solvent or we can use the conjugate base of our acid to start off with. In this case, I'm going to use the solvent. So we can use another methanol molecule to deprotonate that to get us to our final product. And water is the other product that we generated. Now in this case, we have to worry about what's going to happen to the position of the equilibrium as well. So we're using an excess of methanol. This is one way that we can drive the equilibrium. We increase the concentration of one of our starting materials, and that kind of pushes the equilibrium to the other side. The other thing that we can do is we can try to remove the water out of our reaction. And in some esterifications, it's pretty easy to remove the water out. It really depends on the alcohol that you're using relative to the water. It would be difficult in this case because we're using methanol. If we had a higher boiling point alcohol, it would be easier for us to remove the water mechanically from this reaction. So this is an example of a nucleophilic acyl substitution reaction, the Fischer esterification. Hopefully this detailed mechanism will be helpful as you study this chemistry some more.